This is module 3 of chapter 2. In this module, we shall discuss about the central difference interpolation formula. The Newton forward and backward interpolation methods are applicable when x, the argument for which the value of y is to be determined, is either beginning of the table or at the end of the table. But if the argument is at the middle of the table, then the forward and backward difference methods give more erroneous error. So, for this case we need a separate formula, and that formula is known as central difference formula. Lot of central difference formula are developed. Among them, the Gauss central difference interpolation method, Stirling interpolation method and Bessel interpolation methods are widely used. So, in this module we shall discuss these three interpolation method. Like Newton methods, Gauss central difference interpolation formula also are of two types. One is Gauss forward difference interpolation formula and other is Gauss backward difference interpolation formula. Again, the Gauss forward central difference formula are considered for two cases, one for even number of arguments and other for odd number of arguments. Now, let us consider odd number of arguments. So, we have considered 2n plus 1 arguments which are equally spaced, that is the arguments are numbered as x minus n, x minus n minus 1 up to x minus 1, x 0, x 1 up to x n, that is yi equal to f of x I, where I equal to 0 plus minus 1 up to plus minus n, and these values are available in the table. The problem of central difference formula or this particular formula is to construct a polynomial phi x of degree at most 2n, because the number of point is twice n plus 1. So, the degree of the polynomial never exceed 2n, and this polynomial should passes through the points xi, yi. That means, phi of xi equal to yi, where I equal to 0 plus minus 1 up to plus minus n. Alternately, we can say the problem as this one. The following table is given. In this table, x 0 is the middle point and right hand side contains n points and also the left hand side contains n points. But the problem is to find the value of y when x equal to x dash or x double dash, that one is available near the middle point x 0. That means, we have to calculate the value of y when the argument is very close to the middle point x 0 or the argument should be present in the middle of the table. Like Newton forward difference formula, we construct the function phi x as follows. Phi x equal to a 0 plus a 1 into x minus x 0 plus a 2 into x minus x 0 into x minus x 1 plus a 3 x minus 1 into x minus x 0 into x minus x 1 and so on. Note that the factor x minus x 0 is entered at the beginning of the construction of the polynomial. Then we include the factor x minus x 1 to the polynomial. Then we include x minus 1 to the polynomial. That means, to entering the points or the arguments, we give the priority to the right hand side points and then we go to the point for the left hand side. So, for this reason we call this formula as Gauss forward interpolation formula. Here the coefficient a 0, a 1, a 2 are determined based on the condition of interpolating polynomial by substituting the values of x equal to x 0, x 1, x minus 1, x 2, x minus 2 and so on. According to this order, we shall determine the values of the coefficient a i's. Now, we substitute the value of x equal to x 0, then we obtain y 0 equal to a 0. Then we substitute the value of x equal to x 1 to the polynomial phi x, then we get y 1 equal to x a 0 plus a 1 into x 1 minus x 0. That means, y 1 equal to y 0 plus a 1 h, or a 1 equal to delta y 0 by h. Similarly, when x equal to x minus 1, then we get y minus 1 equal to y 0 plus a 1 into minus h plus a 2 into minus h into minus twice h, and after simplification we get the value of a 2 as delta 2 y minus 1 by factorial 2 h square. So, in this manner we can determine the values of a 4, which is equal to delta 4 y minus 2 by factorial 4 h to the power 4, and a 5 equal to delta to the power 5 y minus 2 by factorial 5 h to the power 5, and so on. And lastly, a twice n minus 1 equal to delta to the power 2 n minus 1 y minus of n minus 1 whole divided by factorial twice n minus 1 into h to the power 2 n minus 1, and a twice n equal to delta to the power 2 n y minus n by factorial 2 n into h to the power 2 n. That means, all the values of a's are determined, and using these values the polynomial phi x becomes this expression y 0 plus x minus x 0 into delta y 0 by h plus x minus x 0 into x minus x 1 into delta 2 y minus 1 by factorial 2 into a square, and so on. The last term contains twice n number of arguments or twice n number of factors. So, the entire polynomial is a polynomial of degree twice n, and this is expected because the number of point is twice n plus 1. Now, this formula can be simplified by using a suitable variable s. Again, this set of arguments are equispaced, therefore, we can write x plus minus I equal to x 0 plus minus I h, where I equal to 0 to n, and the new variable s is defined by x equal to x 0 plus s h. Note that the variable s is dimensionless quantity. So, using these two relations, we can write x minus x plus minus I equal to s plus minus I into h. Also, x minus x 0 equal to s h, x minus x 1 equal to s minus 1 into h, x minus x minus 1 equal to s plus 1 into h. So, using these values, the previous polynomial phi x reduces to the following form, and note that in this polynomial each term contains the same number of h in numerator and denominator. So, after cancelling all h, the simplified form of the polynomial phi x is this one, y 0 plus s delta y 0 plus s into s minus 1 into delta 2 y minus 1 by factorial 2, and so on. So, this formula, that means equation 4 or the previous equation 3, is known as Gauss forward central difference interpolation formula, or called the first interpolation formula due to Gauss. So, now we consider even number of arguments, that is twice n number of argument, to construct the Gauss central difference formula in case of forward formula. So, in this case the number of arguments are written as x 0 x plus minus 1 dot 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 x plus minus n minus 1 and x n. In this case there are 2 points is present in the middle position. So, by using the previous formula, that means Gauss forward interpolation formula, we obtain the following interpolation formula for even number of arguments, and that one is phi x equal to y 0 plus s into delta y 0 plus s into s minus 1 into delta 2 y minus 1 by factorial 2, and so on. So, after simple simplification or modification, this formula becomes this one, y 0 plus s delta y 0 plus s into s minus 1 into delta 2 y minus 1 by factorial 2 plus s into s square minus square whole into delta 3 y minus 1 by factorial 3, and so on. So, this is the final form of the Gauss forward difference interpolation formula for even number of arguments. Now, we present the error terms for Gauss forward central difference formula for twice n plus 1 arguments, and this error expression is obtained by the general error formula presented in module 1 of this chapter, and that one is x minus 1 up to x minus x n into twice n plus 1 derivative of f at xi whole divided by factorial twice n plus 1. So, substituting the value of x in terms of s, the entire expression is simplified as s into s square minus 1 square up to s square minus n square into h to the power 2 n plus 1
into 2n plus 1 derivative of f at xi by factorial 2n minus 1, where the value of x, that means xi, lies between the maximum and minimum among the arguments. So, we can write min x minus n minus 1 up to x n less than xi less than max of x minus n minus 1 up to x n. Similarly, the errors in Gauss forward central difference formula for even number of argument is given below. Ex equal to s into s square minus 1 square up to s square minus n minus 1 square into s minus n into h to the power twice n into twice n derivative of f at xi by factorial twice n, and xi lies between the maximum and minimum values of the arguments. Now, we go to the another important formula called the Gauss backward difference formula, and this is for 2n plus 1 argument, that means for odd number of arguments. So, here the number of points is 2n plus 1, that means there is only one point, that one is denoted by x0 at the middle position, and the other points are denoted by x1, x2 up to xn and x minus 1, x minus 2 up to x minus n. So, in this case the polynomial phi x is constructed as per following rules, that means phi x equal to a0 plus a1 x minus x0 plus a2 x minus x1 into x minus x0 and so on. Note that here the factor x minus x0 enter at the beginning of the construction of the polynomial, but x minus 1 factor is appears in the polynomial before x minus x1. That means, we have given the priority to the left hand points x minus 1, then we go to the point x1, and then we include the point x minus 2, that means the factor x minus 2, and then we include the factor x minus 2. So, in this reason this formula is known as Gauss backward difference formula. Here a0, a1, a2 up to a twice n are the constant, and their values are to be determined according to the condition of interpolation. So, since the arguments are equispaced, therefore, we can write xi equal to x0 plus ih and x minus j equal to x0 minus jh for all I and j are equal to 0, 1, 2 up to n. Thus, xi minus x minus j equal to I plus j into h, and x minus I minus xj equal to minus of I plus j into h. Now, to find the values of ai, we substitute the values of x equal to x0 at the beginning, then we substitute x equal to x minus 1, then x1, then x minus 2 in this order. So, using this order or maintaining this order, we obtain the value of a0 as y0, and then phi of x minus 1 equal to a0 plus a1 into x minus 1 minus x0. That means, a1 equal to y0 minus y minus 1 whole divided by h, and this is nothing but delta y minus 1 by h. Phi x1 equal to a0 plus a1 x1 minus x0 plus a2 into x1 minus x minus 1 into x1 minus x0. That means, a2 equal to delta 2 y minus 1 whole divided by factorial 2 into h square. And similarly, we obtain the value of a3, and which is equal to delta 3 y minus 2 whole divided by factorial 3 into h cube. And the other values can be obtained by similar way, such as a4 equal to delta 4 y minus 2 by factorial 4 h to the power 4, a5 equal to delta power 5 y minus 3 by factorial 5 into h to the power 5, and so on. Lastly, a twice n minus 1 equal to delta to the power 2n minus 1 y minus n by factorial 2n minus 1 into h to the power 2n minus 1, and a twice n equal to delta to the power 2n y minus n by factorial 2n into h to the power twice n. So, we determine all the values of a using the condition of interpolation. Now, substituting these values, we get the simplified form of the polynomial phi x equal to y0 plus x minus x0 delta y minus 1 by factorial 1 h and so on. Again, the arguments are in equispace. So, this formula can also be simplified by introducing a new variable s. Now, we substitute x equal to x 0 plus h. Therefore, x minus xi by h equal to x minus x 0 minus I h whole divided by h, and this is nothing but s minus I. Similarly, x minus I by h is equal to s plus I, and this is true for all I equal to 0 to n. So, using this notation, the above formula becomes phi x equal to y 0 plus s into delta y minus 1 plus s into s plus 1 by factorial to delta 2 y minus 1 plus s plus 1 into s minus 1 by factorial 3 delta 3 y minus 2 and so on. So, this is the simplified form with the help of the new variable s. So, this formula is known as Gauss backward interpolation formula or second interpolation formula for Gauss for odd number of arguments. Now, for the even number of arguments, that means twice n number of arguments, there is two middle points x 0 and x 1. So, the arguments are numbered as x 0 x plus minus 1 up to x plus minus n minus 1, and the last argument is denoted by x minus n. Since the arguments are equispace, therefore, we can write x plus minus I equal to x 0 plus minus I h, where I equal to 0 to n minus 1 and x minus n equal to x 0 minus n h. So, using this notation and proceeding as in the previous case, the Gauss backward interpolation formula for even number of argument is phi x equal to y 0 plus s into delta y minus 1 plus s plus 1 into s by factorial 2 into delta 2 y minus 1 and so on. So, this is a polynomial of degree 2n minus 1, where the new variable s is equal to x minus x 0 by h. Here also we calculate the error terms in Gaussian backward central difference formula. For odd number of arguments, the error term is equal to s plus n into s plus n minus 1 up to s minus n into h to the power 2n minus 1 into 2n plus 1 derivative of f at xi by factorial 2n plus 1. Similarly, for even number of arguments, that means for twice n argument, the error term is s plus n into s plus n minus 1 up to s minus n plus 1 into h to the power twice n into 2n derivative of f at xi by factorial twice n. Note that the xi lies between the minimum and maximum values of the argument, like the previous case.
So, we have derived 4 formula due to Gauss, 2 formula for Gauss forward difference interpolation formula and 2 formula for Gauss backward difference interpolation formula. Now, using these 4 formula, we can derive another central difference formula called Stirling central difference interpolation formula, and another is called the Bessel central difference interpolation formula. And these 2 formulas are computationally efficient compared to the Gauss 4 formulas.
Now, we discuss Stirling interpolation formula. This formula is very simple. If the Gauss forward and backward difference formula are available for odd number of points, that means the Stirling formula is applicable when the number of arguments is odd and they are equispaced. So, this formula is derived from the Gauss forward interpolation formula, that means that one is denoted by phi x forward, and phi x backward indicates the Gauss backward interpolation formula for twice n plus 1, that means odd number of arguments. By taking average of these 2 polynomials, we obtain the Stirling interpolation polynomial, and that one is given by phi x equal to phi x forward plus phi x backward by 2, and after simplification of this expression, we obtain the final expression for Stirling central difference formula, that one is equal to y 0 plus s by factorial 1 into delta y minus 1 plus delta y 0 whole divided by 2 plus s square by factorial 2 delta 2 y minus 1 plus dot dot dot, and lastly s square into s square minus 1 square, s square minus 2 square dot 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 a square minus n minus 1 square whole divided by factorial twice n into delta to the power twice n y minus n. So, this is the final form of Stirling central difference interpolation formula. So, it is seen that this formula is very simple if the formula Gauss forward interpolation and Gauss backward interpolation are available for odd number of arguments. Now, we observe three important points for Stirling interpolation formula. The first one is the Stirling interpolation formula is applicable when the argument x for which f x is to be calculated is at the center of the table and the number of arguments is odd. And second observation is if the number of arguments in the given tabulated value is even, then discard one endpoint from the table to make odd number of points such that x 0 becomes the middle of the table. That means, the Stirling interpolation formula can also be applicable for even number of points. The third observation is very important. It is proved that the Stirling interpolation formula gives better result, obviously the approximate result, when s lies between minus 0.25 and 0.25. So, it is suggested that assign the subscript to the point in such a way such that s, which is equal to x minus x 0 by h, satisfies this condition. Now, I go to another interpolation formula called Bessel's interpolation formula. It is also obtained by taking the average of Gauss forward and backward interpolation formulae after shifting one step of backward formula. So, let us consider twice n equispace argument as x 0 is taken as the middle one and there are n points to the right of the middle point x 0 and there are n minus 1 point to the left of the point x 0. So, for this representation or for these points, the Gauss backward difference interpolation formula, that one deduced in equation 8, is stated below. Phi x equal to y 0 plus s into delta y minus 1 plus s into s plus 1 by factorial 2 delta to y minus 1 and so on. So, this is the Gauss backward central difference formula for this assumption, that means x 0 is the middle point and right side contains n point and left side contains n minus 1 point. But we would like to renumbering the points as mentioned below. Now, we consider x 1 with the middle arguments instead of x 0, that is the number of points to the right of x 1 becomes n minus 1 and number of points to the left of x 0 becomes n. That means, we have to shift the points one step to the right. So, for this shifting, the new shifted arguments are denoted by red color or marked by red color. That means, x 0 is now becomes x minus 1, x 1 become x 0 and so on. So, in this substitution or in this shifting of the arguments, x minus x 1 by h becomes s minus 1. That means, we have to replace s by s minus 1 and we have to increase the indices of equation 2, that means the equation of previous slide, by 1 to get the Gauss backward difference interpolation formula for this new numbering of the arguments. And for these arguments, the Gauss backward difference interpolation formula becomes phi 1 x, the new formula is denoted by phi 1 x, which is equal to y 1 plus s minus 1 into delta y 0 plus s into s minus 1 by factorial 2 delta to y 0 and so on. So, this is the Gauss backward interpolation formula by shifting the arguments. Now, we obtain the Bessel's interpolation formula by taking the average of the formula 11, that is discussed in previous slide, and Gauss forward interpolation formula for even number of arguments. That means, phi x equal to phi 1 x plus phi x forward whole divided by 2. That means, this is the average of these two formula, and after simplification this formula becomes y0 plus y1 by 2 plus s minus half into delta y0 and so on. But we see that s minus half, that particular factor is appears in all the terms. So, we can simplify this expression by using a special variable, and we have used a new variable u to represent the factor s minus half. That means, u equal to s minus half equal to x minus x0 by h minus half. So, using this notation, using this new variable, the above formula becomes y0 plus y1 by 2 plus u delta y0 plus u square minus 1 by 4 by factorial 2 into delta to y minus 1 plus delta to y0 by 2 and so on. So, this is called the Bessel central difference interpolation formula, and this is the final form of this formula, and this formula is applicable for twice n, that means the even number of arguments. Now, it is noted that the Bessel formula gives best result, best approximate result when u lies between minus 0.25 and 0.25, that is s lies between 0.25 and 0.75. Again, the Bessel central difference interpolation formula is used when the number of arguments is even and the interpolation point is near to the middle of the table. Now, we consider one example to illustrate the Stirling interpolation formula and Bessel interpolation formula. The set of values of x and y are given as a tabular form. Our problem is to find the value of y when x equal to 1.55 using the Bessel central difference formula, and also we have to determine the value of y when x equal to 2.30. For this table of values, we construct a central difference table which is given below. The first column represents the indices of the arguments, second column represents the values of x, that means the arguments, the third column contains the value of y, fourth column contains the first order central differences, the next column represents the second order central differences and so on. So, in this case x equal to 1.55, and so we consider x0 equal to 2.0 because 1.55 is close to the point 2 for this table of values, and hence s equal to 1.55 minus 2 by 0.5, 0.5 is the step length h, which is equal to minus 0.9, and the Bessel formula gives y equal to y0 plus y1 by 2 plus s minus half into delta y0 and so on. So, by using these values, that means the value of y0, y1 and all other differences and the values of s, and after simplification we obtain the value of y when x equal to 1.55, and that one is equal to 13.5829, and this value is correct up to 4 decimal places. Now, we use Stirling formula to calculate the value of y when x equal to 2.30. So, in this case is x equal to 2.30, and also we consider x0 equal to 2, and in this case the value of s equal to 2.30 minus 2 whole divided by 0.5, and that one is equal to 0.6. The Stirling formula is yx equal to y0 plus s and average of delta y1 and delta y0 plus s square by factorial 2 delta to y minus 1 and so on. So, by putting the values of delta y0, delta y minus 1, delta 2 y minus 1, delta 3 y minus 2, delta 3 y minus 1 and the values of s, we get the values of y at x equal to 2.30, and that one is approximately equal to 16.2773, and this value is correct up to 4 decimal places.
So, in this module we have derived 4 formula due to Gauss, and based on these 4 formulas we have derived other 2 central difference formula known as Stirling formula and Bessel formulas. All these formulas are applicable when the arguments are equispaced, and all these formulas are similar to the Newton's formulas, and these formulas are applicable when the arguments for which the value of y is to be determined is at the middle of the table.